Okay, so
Recording
here
in
we are,
progress.
chapter 4. You guys hear me?
Yeah.
Where can we find the recordings?
Um,
On Moodle?
Yeah, Moodle.
Okay. Just because I wasn't feeling well on Sunday, so I left early.
We might start chapter 5 today.
If we started, would we be able to upload the slides before we start it?
Because it's not
Yeah, I
on
take
Moodle at
notes
all.
on
We
the
all
slide.
take
Yeah,
notes on the
that's
slide.
a good point. Well, we'll see. Yeah, right.
You'll upload it during our break.
Yeah, maybe we'll have a break. Okay, so multi-threaded server architecture. We talked about this a little bit. The server is sitting there listening for requests for information. And the minute there's a request for some connection, he creates a thread, a child process. We kind of did this in the lab. We did fork. That's an actual process. But here he creates an additional client for dealing with. There's an additional program to deal with the client's request. The client gives a request. He creates a new thread to service the request, and then the server goes back to listening again. But the thread will handle the talking with the client. Well, the obvious benefit of this is responsiveness. I would say you're freeing up the server to deal with the next request. Oh, cheaper than process creation economy, cheaper than process creation. Okay, we would do it with fork with a new process. You could also do with a thread, which is lightweight, which is less copy. Process could take advantage of multi-process architecture. Right. All right. So can multi-processes also, but multi-threads, so you can run them on different processes. May allow. We'll look at the first one. May allow continued execution of part of the process block, especially important for user interfaces. Right. If you have every little thing of the process being done by different threads, then if one gets stuck, everything won't be stuck. Whereas if you had only one thread, then the minute one thing got stuck on something, the whole program would be stuck.
Wait, so what was it with multiple threads?
That's responsiveness.
What was it exactly with the?
Responsiveness is saying if one part of the process gets stuck for whatever reason, then if you would have only one thread, then the whole process would get stuck. But this way, by having multiple threads it's like having lots of little minions doing your program for you. So if any one of them gets stuck, the other ones can continue working. Okay. Multi-core, multi-processor systems putting pressure on programmers. Challenges include, right? In other words, if you're a programmer and you want to write a program in a multi-core environment, then you've got to think in a different way. You've got to think what processes can I have running at the same time. It's a harder way to think as a programmer. You've got to divide activities. Data splitting. One portion of the data is used to develop predictive model, and the other to evaluate the model's performance. The training set is used to fit the model and validation for the evaluation. So, yeah, I think I added this to the slide. Data splitting, what is that? That means that you basically, how should I say this? Let's say you want to predict the weather. You want to come up with a model to predict the weather. So you use some of your data to create the model based on its past weather, things. If it was 25 degrees, then the next day it would be 26 degrees. Whatever your data is, you use to predict the future. And then you use the other half of the data to check if your predictions are correct, because you actually have the data. You're checking last year's data. So you have the first half of the data, the first 6 months of the year, the second half of the 6 months of the year. So you use some of your data to create a model the first 6 months, and then you use that to predict the second 6 months. So the second 6 months, you already have the data for it. So you can see if your model correctly predicted the second 6 months, for example. That would be called data splitting. And you could do this like, I guess the idea here is that you would have two processes. One predicting and the other one checking the predictions if they're correct.
So data splitting allows you to do multiple things at once.
Well, data splitting, no. Data splitting is the concept of using some of your data to create a model and another set of your data to check the predictions that that model made, see if they're accurate.
Why is that a challenge?
Why is that a challenge? Well, it's complicated to program. It's a challenge to the program. It's just more difficult. I don't know. Data dependency, read after write. Here, right. This is they're saying this is a problem with multi-threaded. Look at this. A equals 3, B equals A. And then C equals B. What if I did these in 3 different threads?
So then it'd be a problem.
Then exactly. Then C would get perhaps the old value of B. Or B would get the old value of A. Now this here I have a thing where I want a certain order. A equals 3, and then B equals 3, and then C equals B. So if I'm going to I'm saying this is a challenge to multi-threaded because this is a challenge to multi-threaded because if I do this simultaneously, if the one thread is doing A equals 3, one thread is doing B equals A, and one is doing C equals B, then the result, there's that. Then I'm going to get. I don't know what result I'm going to get. I don't know what one will finish before the other. I don't know. The order is important in this case, but yet when I do things in parallel, I lose all control over the order.
Are you saying the problem isn't doing them in different threads, it's doing them in the same thread?
No, I'm saying no, if you do them in the same thread, everything will be fine. But when I split them into different threads, then I have no way of knowing the order. And maybe B will get the value of A before I change A to 3. Maybe A used to be 2. And if I do this line first, B equals A, the B will become 2 instead of 3. But I wanted it to be in order. So you can't just take any program. The point is you can't just take any program and divide it up into 3 parts and say different threads will do different parts. Because sometimes those parts, one is dependent on the previous one. I mean, this is a trivial example. But the point is you may have a part of your program that depends on the result of the other part. And if they're running in parallel, so you're going to have to, you have to do something called a join. You have to wait for one part to finish before you start the next part. If we go back to data splitting, I think the challenge there is that you don't want to evaluate the data, the predictions, before you predicted them. In other words, one part is to predict the value, another part is to evaluate them. There has to be a certain order there. So that will be a problem with multi-threaded. I'm not sure what the difference here between what they're trying to say here between parallelism and concurrency. Parallelism implies that a system can perform more than one task simultaneously.
But what's the point if what you were saying about when it runs, when you have the read after write within multiple threads, if it runs parallel, that's also a problem. It only works if it runs in the same thread.
Well, this case, you could run in one thread or you could run in 2 threads. But if you're going to run this in 2 threads, then you're going to have the B equals A wait, do some kind of wait operation where you wait for the first thread to do A equals 3. So even though they're running in parallel, you're going to have to sort of synchronize them. So don't continue until the other one finished. That's that's a complication of parallel programming. You have to do synchronization. Whereas if everything is running sequentially, so you know that it's not going to go to the next line of your code until the previous line. Anyway, what they're trying to say is, but parallelism is the most basic concept. Things are running in parallel. Concurrency means that not only are they running in parallel, but one is making progress. I think we'll see later what progress, but it's getting near the solution to the problem, to whatever problem. All right, I'm going to skip this. Here's concurrency versus parallelism. Okay, so I said a little bit different. I'll say a little bit. Concurrency means that really you have only one core. It's not true parallelism. In other words, they're all making progress. Task 1 and task 2 and task 3 and task 4 are doing some of their tasks, right? Task 1 did something here, and then he gets another time slice over here. So he's making progress. They're working concurrently, but not simultaneously. Parallelism is where they're running simultaneously. Task 1 and task 2 are running at the same time. Task 3 and task 4 are running at the same time. So they're all making progress, but they're doing it in parallel here. Whereas here, they're making progress, but not in parallel. That's called concurrency.
So parallelism is running simultaneously.
Right. And concurrency means that they're all progressing, but not simultaneously. They're not running simultaneously.
So
I don't really understand what that means. They're saying the same thing.
Well, look at the picture. T1, T2, T3, T4. This means this line means time. This is not notice this area that says time. So that
So it
means
sounds like
it goes on.
one at a time.
In the first period of time, only T1 is running. The second period of time, only T2. So that's even that. So you say, well, why is that concurrent? That's one after the other. It's serial. One and then the next and the next in a series. But the idea is that they're progressing towards their completion together. Each one gets a little piece of time, 20 milliseconds, 20 milliseconds, 20 milliseconds, 20 milliseconds. And then we go back and give the first one 20 milliseconds. So that's called concurrency. As opposed to T1 running and finishing all of his job before T2 ever gets started. T1 maybe takes many 20 millisecond slices to finish. But you're stopping. This is multitasking. Whereas parallelism, T1 and T2 are running at the same time on two different cores, on two different processors. Is that better? Gabby?
Yeah, I get it now.
Okay. This is all very basic. This is all pretty obvious, I think, at this point. Single thread has single thread, and here's your processor with your code, your data, your files, etc. Here is your multi-thread. This is a process, you see. The process has all this stuff. Notice that these three threads share the code, data, and files. In other words, the code section, remember we said there's multiple PCs, multiple program counters, pointing to different areas of the code. They're sharing this code, but the registers, you see here registers, they each have their own registers, their own stack. So they're kind of like independent programs, but they're sharing the files, the data, and the code. Now, as the code is in memory, the data is in memory, and the files on the disk, they're sharing. Whereas here, I have just, each thread here has everything. If I would have If I want to have 3 threads, I'd have to do this whole picture 3 times. That would be a single thread process. Now this Amdahl's law we remember from Mivnei HaMachshev. Remember Amdahl's law?
Oh, I hated that one. I couldn't ever figure it out. It was like all this different type of math.
It's very simple, really.
I know, but it seems so.
It seems complicated. It's really so simple that it's hard, that it's confusing if you have it written down. It's really very simple.
And that's why it was confusing.
Yes, that's right.
Are we gonna have to know his law for the exam?
No.
Okay, good.
But S is the serial portion, N is the processing cores. So
Serial portion meaning,
the part that can't be speeded up. Remember this?
yeah, there was a part that you can't speed up and a part,
That
how much
could-
you can speed up and how much
that
you
you
can,
could
and
speed up,
what's the
right.
percentage, what would be the total.
That's right. So let's see this example. If application is 75% parallel, 25% serial. So the 25% serial can't be speeded up. Moving from 1 to 2 cores, what does it result in? It results in a speed up of 1.6 times. Why? Well, let's think about it intuitively. 75% of it was doubled in its speed, or halved. It took a half amount of time. But 25% took the same amount of time. So it's now going to be 25 plus half of 75. It's 37. That's so 1 over 57, 50, whatever, you have to do the math. But it comes out to be a speed of 1.6 times. In other words, it's not going to be twice as fast. If the whole thing, imagine like this, the whole thing could be parallelized and into 2 things. If it was 100% parallel, then it would be 2 times as fast. But it's not quite 2 times as fast, only 1.6 times as fast, because only 75% of it can be parallelized. That's the idea.
What?
Basically, you add 25 plus half of 75, and you get 50 something, or you get 60 something, 62%, and then you think it'd be 1 over 62. I think we get 1.6, something like that.
What is this calculate?
This is calculating how much speed up you'll get if you parallelize part of your program. I don't want to go over it because you guys did this already in another class. I teach it in another class in a different way. And when I teach the architecture first, I'll teach that more in detail. All right, this is. All right. So now we're going to talk about user threads versus kernel threads. Many user level threads map to a single kernel thread. That's many to one. In other words, the kernel can only run 1 thread at a time. So if I have multiple threads running, how will that work? I only have one, the kernel can only run 1 thread at a time. So he'll run just one of these threads, but if one of them gets stuck, then all of them will be stuck.
I thought the whole point of threads is that there's a problem in one, it doesn't cause a problem in the others.
Right, that is the point. But that's only if you have real threads. If you really have threads running in the kernel, but if you have like kind of a simulation of threads, that's kind of what we're describing here. Many to one is really like a simulation of threads. We don't really have threads. really, from the kernel's perspective, he's just running one thread. He's only really running one thread at a time. Multiple threads may not run in parallel on multiple core systems because only one may be in the kernel at a time. Right, even if I have multiple cores, I can only put one thread in the kernel at a time. Few systems currently use this model. So forget about that. That's a bad system. Here is a more logical system. Each user level thread maps to a kernel thread. In other words, the kernel can run each thread independently. But that means that the kernel has to handle all these threads, has to know about all these threads and manage all these threads. So that can be, you'll have to limit the number of threads. On a normal Unix system, you can only have 64,000 processes. But what if each of those processes has 2 threads? So if there's, in this system, again, 64,000 processes is the maximum. Let's say each of those processes, like in this picture, has 4 threads. So that would work, you would be able to do that, 64,000 processes, each with 4 threads. That would work well, because as far as the kernel is concerned, there's really only one process going. But if you have this system, where the kernel knows about every thread, then if you only can have 64,000 processes, you can also only have 64,000 threads. And then you'd only be able to have 16,000 processes, each with 4 threads. This is an example. In other words, you're limiting. It's better because now you have like multiple threads running in the kernel, but they take up overhead. They take up management. This is a more complicated system, which is many user threads to many kernel threads. But notice the number: 4 user threads to 3 kernel threads. So what does that mean? That means that the kernel can run, like if the kernel can run on, let's say on this K here on the right, he can run either, any one of these threads. So I can't run more than 3 at a time. But if one gets stuck, I can skip to another one. And then there's a 2-level model where you have sometimes a user thread goes to the kernel thread, and also a pool. Well, you do 2 things. Sometimes they're direct. One has its own kernel thread, and sometimes you have many. You also a pool. In other words, some of the threads are pooled together, and some of the threads have their own kernel thread.
But in total, the number of threads that are going to be run are going to be dependent on the number of kernels. So they get to choose which one, but there'll always only be 3 running at a time if you have 3 kernels.
Right. In this case, in this case you have 4. If you think about it, you have 4 kernel threads. One is like permanently matched to this thread. And here, this is like a pool of kernel threads that are running on these, a pool of user threads running on these 3 kernel threads. So we have 4 actually at the same time.
So in this case, if the user thread that was connected directly to a specific kernel thread, then if there's a problem with that user thread, it can't just move on to another one because.
Yeah, he's stuck. He's stuck with him. This kernel thread is occupied by this thread. So if this thread is blocking, let's say, waiting for I/O, so he's just waiting. But here, if this one's waiting for if this thread is waiting for I/O, he can move on to he can run a different one. That's it.
In this case, could we have more threads than kernels, like the way it was in the first option? Because like he could just, I guess, switch between them.
Well, so we have 4 user threads and only 3 kernel threads here. In this one. And we have a total of 4 and 5 user threads.
Is that what it means to get debound?
To get what?
Bound.
P bound?
Bound. It says on the slide bound,
Oh,
but it has to wait to get stuck.
bound to a kernel thread. No, that doesn't mean bound like, right, we used the same word bound a different way before, like IO bound. Here it just means connected to. Similar, except that it also allows a user thread, that's this case, to be bound to a kernel thread, that he's permanently connected to this kernel thread. So here's just to know what there is a thread. Pthreads API is in Linux, and it's a specification, not an implementation. What that means is it's specifying how threads should be done on any kernel, on any Unix system, but it doesn't tell you exactly how to do it. It doesn't tell you how to do it. It tells you how the interface should be. So here's a piece of code where first I basically, your pthread TID is like your PID, your thread ID. And basically that's an integer. The key line here is, this is all irrelevant, this is not so important here. Here, pthread create. Here is my function called pthread create, which I give it the TID and whatever attributes I defined over here. Here I just defined like default attributes. And runner, what's runner? Runner is this program. Well, where is it? Here. Runner takes a parameter, A2I means ASCII to integer, it converts that ASCII number into an integer. It does some kind of loop. It basically it just does busy work. It does make some kind of loop and adds up some numbers. And so it's not really important what this running program does. But the point is this line here. This is the only line that and this is the main line to understand. I created the thread. I told it where the ID, when it creates it, has to give an ID value to it. It should put it in this variable called TID, which I defined before here. And the attributes, like I said, are default. But here, runner means when this thread starts up, what should it do? It should do this program, this function called runner. That's just what you see on the bottom of the page, on the bottom of the slide. So that's how I can create in a program like a separate thread to run anything I want, to run a function. And I give it, what is argv0? I give it a parameter. That argv of 1 is the param that is here in the function, this param. So basically I can, with this pthread create, I can create a thread, give it a function to run, and pass that function to parameter all in one shot. And then I have this join here. Where's this join? Here, pthread join means wait for the thread to finish. Pthread join means don't do anything until the thread finishes. So it's actually kind of pointless because the father is just waiting around for the thread to finish. But you could have multiple threads. You could call this in a loop. You could call many, many threads to do things, and then you could wait. And that's, I think, what he's trying to do over here. Pthreads code for join 10 threads. Here it is a loop where he does pthread join, keeps looping here 10 times. Great number of threads, 10. He loops 10 times and does a pthread join on each of the threads. Right, this. I don't know. This is all Unix, how to do this stuff. Here you have pthread cancel. That means to end the process in the middle of its run. before it has finished, terminating a thread before it has finished. So I can cancel it based on this TID. Right, a thread itself can say that he's gonna ignore that cancellation request. And at a certain point, he'll accept it. In other words, he might be in a critical section. The thread might be in a section where he doesn't want to stop in the middle. But you wrote that program, so you wrote it, but it wouldn't accept the cancel at a certain point. I'm skipping a little bit here. Yeah, that's it. So I did make this very short. All right, let's take a break and I will get 5 for you guys.
How long break we taking?
Let's take 15 minutes.
See, you are on the Zoom.